joint uh, probability mass functions will be given to you, and in that case, uh, given to you, or you may have to form the joint uh, probabilities in a tabular form. So once it is done, you can get the marginal probability mass function of the random variable x and y. And having done that, you can calculate various quantities which are involved in calculating the correlation coefficients. So mainly you require mean, variance of the random variable x, and then you require the covariance term, so which is expected value of xy minus e of x, e of y. So once you calculate all those quantities, you can finally get the correlation coefficient. So it will be always lies between -1 and +1. So in case if you are getting the value greater than 1, then are not in the range of -1 to 1, then some error is there and you can recheck your calculation. So having done that, uh, there are a few observations I want to make it, that suppose we have a linear relationship between x and y. Linear relationship means y equal to a plus bx type of relationship. Okay, y equal to a plus bx is a line. So y equal to, say for example, I have taken y equal to 2 plus 3x. And we know the mean of x, variance of x, and in that case, how to find the correlation coefficient. So here, as you will see, that expected value of mu, we are assuming. So expected value of y you can calculate from this relationship. So 2 plus 3 mu. Okay. Then variance of x equal to sigma x square is given to you. So variance of y will be variance of y equal to variance of 2 plus 3x, and variance of constant is 0, and it is 3 square variance of x, so 9x square. So covariance xy, as you can see, we can calculate using e of xy minus e of x, e of y. Since y equal to 2 plus 3x, so I can calculate this particular quantity first. So e of xy is calculated here. So e of x equal to that, you substitute the value of y, which is 2 plus 3x here. So I have just kept that quantity here. Okay. So now you just manipulate. So it will become e to the expected value of 2x, then expected value of 3x square. So constant term you can take out, and then this will become 2 mu, and this will become 3 expected value of x square. So how to get expected value of x square? Because variance of x is equal to expected value of x square minus e of x square. So many a times, in order to calculate expected value of x square, we can write variance of x plus e of x whole square. So this result will give you sigma x square plus mu square equal to e expected value of x square. So I can get it from here. So 3 sigma x square plus mu square. So covariance, now you can calculate because these quantities are known to you. So ultimately you will get 3 sigma x square. So all the quantities are known. 3 sigma x square, square root of sigma x square into 9x square. Okay, because variance of y we have already calculated. So under the square root, we have sigma x square into 9x square. Here it is multiplication sign. So if you calculate, it will come 1. So basically, correlation measures the strength of linear relationship. Okay, I will show you this observation by means of the data also. So whenever we have a perfect linear relationship between X and Y, the correlation coefficient will be always 1. Okay. So basically, rho, as I told you, rho could be between -1 and 1. So rho equal to 1 means when uh, X increases, Y also increases. And rho -1 indicates that when X increases, Y decreases. And rho equal to 0 means, here I am going to show you one example, that if the relationship is not linear. Say for example, in this case, here if you look at here, if I define Z as a normal variant, okay, with mean 0 and variance, and uh, I have another random variable Y, so Y equal to Z square. So I want to find the correlation between, say here I can define this as X also. Say X is my Z, normal 0, 1, Y is Z square. So I want to find what is the correlation between rho between X and Y. So basically I want to find rho X and Y. Since X is Z, so Z and Y, the way you want to write, you can do it. But here, basically meaning is that one variable is Z, another variable is Y, which is Y equal to Z square. I want to find the correlation between X and Y. So certainly X and Y means I will write, uh, I will write covariance XY and divided by variance of X, variance of Y. So here, uh, it is Y and Z. Okay, Z is basically X. So covariance YZ square root of sigma Y square Z square. So how to get it? Covariance YZ. So covariance YZ, you can write expected value of YZ minus E of Y into E of Z. Since Y equal to Z square, so expected value of Z square into Z, and expected value of Z is 0, because Z is normal 0, 1. Okay, Z is normal 0, 1. So mean of Z is 0. So this side is 0, and this becomes expected value of Z cube. Now expected value of we already know that all the odd order central moments are 0. So Z has mean 0. So it becomes expected value of Z minus 0 cube. So expected value of Z cube, it is 0. So correlation is 0. So when there is uh, absence of linear relationship between the two variable, that as you can see here, the relationship between the two functions is it Z, this is Z and this is Z square. Basically, it is a function something like that, parabola. Okay, it is like that. Okay, so in this case, the correlation is 0. So I will take some uh, example with the help of data, so that you can observe these facts also. So now in statistics, we have two different symbols. One, we use capital rho to indicate the correlation coefficient between X and Y, and it is known as the population correlation coefficient. Basically, there is a concept of the population and the sample in statistics. Usually, the population is considered to be a uh, large, uh, large set of an entity. Entity could be a human population or a student population. The way you define the population means there is some similarity among the uh, various elements of that group. So population correlation and sample correlation means you take a sample from the population, and you find out what is the correlation coefficient between X and Y. Now, in order to compute the population correlation coefficient, this rho, we must have the joint distribution of x and y. The way here I gave you that we had a form of joint probability mass function, then you can calculate the population correlation coefficient. But in practice, getting the joint distribution of two random variable x and y are difficult. So we define the uh, sample correlation coefficient, which is known also as Karl Pearson correlation coefficient. But here, before we proceed there, proceed to define the sample correlation coefficient, we have earlier seen basically this least square method you have done in the mathematics 2, where what is the objective that you have two sets of observation x and y. So x1 y1, x2 y2, x3 y3, xn y1, say height and weight, or whatever it may be there. Okay, one variable is dependent variable and another is independent variable. Okay, so we have a pair of observation and observations are there, and these n observation we just plot. So on the x-axis and y-axis, these dots indicates the observations x1, y1, x2, y2, xn, yn. Okay, so this we call basically it is like this. You can just plot here something, some point here, some point here, like that. Okay, so these dots indicate the points. Now our objective is to fit a line. Okay, so with the help of this data, we have to fit a line. So line, this particular line, okay, which we represent by y equal to a plus bx, and why we put a cap. Cap indicates means this is a estimated line. And how did we estimate this line? With the help of this data x1 y1, x2 y2, x3 y3, xn yn. Okay, so now the question is that how to get a and b. Okay, because once you are fitting a line means you need to get the intercept as well as the slope. So in statistics, at many places, basically this cap is used to indicate that these values has been estimated, okay, from the data. And basically there is another area which is known as the statistical inference. Means you have to draw the inference based on the sample for the population. So there is a theory of estimation, theory of testing of hypothesis, and many more things. So that those things are not the part of your course. So here, so this fitting of the line. So as I told you, this is the estimated line. If I theory of least square method we use, and that you have done in maths too. This is the error part. If I take any particular point, so actual value corresponding to xi is y, and the estimated value will become yi cap. So this is the amount of error. So if the point is here also, then it will be negative. Some otherwise it will be positive. So basically the least square method tells you that minimize the sum of squares of the error. So the derivation I have given in the last few pages of this sheet. It has already been done in your Maths 2 course. So I'm not going to discuss here, but at the end I will explain you. So you get the, from the data you get the slope, you got the b, and you got the a. Okay, y bar and x bar indicates the average value. So we have got the line. So in this case, we can also define the correlation. Means what is the relationship between y and x. So there is a measure which is known as the Karl Pearson coefficient of correlation, and it is usually represented by small r, and it also lies between -1 and +1. So it is defined as summation xi minus x bar, yi minus y bar, and square divided by the square root of summation xi minus x bar whole square into summation y minus y bar whole square. Now, uh, there is another way to represent that. Since there are n observation, I can define 1 by n. Uh, I can divide by n, numerator and denominator. So 1 by n uh, summation xi minus x bar yi minus y bar. So this particular quantity is known as the covariance xy, and this quantity is known as the variance of x. This quantity is the variance of y. If you remember that given n observation or n observations, so we calculate the mean by sum of the observation divided by the number, and we calculate the standard deviation or variance using this formula 1 by n summation xi minus x bar whole square. So usually this is the formula which is used to calculate the correlation coefficient, and we normally represent by covariance xy by sigma x sigma y. So it is similar to what we have discussed earlier. Only difference is that here you are computing correlation with the help of the data. Means you have a pair of observations for x and y, where y is the dependent variable, x is the independent variable. So R can be calculated from here. So there is a simplified way to calculate that. If you expand this, then it will be summation xi minus y minus n x bar y bar, and these are the simplified formula for calculation of correlation coefficient. So as you can see, uh, the uh, the line which we have earlier derived, this uh, this quantity I can represent in terms of the covariance. Okay, so if I divide by 1 by n, so it becomes covariance xy divided by sigma x squared. Okay, so the slope is equal to the covariance divided by sigma x sigma y square. And if I want to represent this in terms of the correlation, so here as you can see, covariance xy is equal to r sigma x sigma y. Okay, here. So from here, if I substitute the value of covariance xy, which is equal to r sigma x sigma y, so here r sigma y sigma x square, so it is r sigma y sigma. So this is a relationship between the slope and the correlation. So if any one of the quantity is known, one can obtain the another one. So we have got the line. So as I indicated, R measures the strength of linear relationship of our degree of linear relationship. Means how this data, if the data, how this data are close to this line. Okay, so it measures the strength of linear relationship. So as you can see that sometimes here it is x-axis, here it is y-axis. So r greater than 0 means all your data are in this that having a trend. Trend means as x increases, y increases. So it shows that r will be greater than 0. Sometimes basically using the scatter diagram. Scatter diagram means you remove this line and just plot the data. So that gives you an indication whether the r will be greater than 0, r will be less than 0. Okay. So here as x increases, y increases, then in that case correlation will be greater than 0. And with the help of this data, you can fit the line. And the purpose of this, what is the purpose of this line? Purpose of this line is that, say suppose your data is up to here and here only, but if you want to predict a future value, say corresponding to this, what will be corresponding y. So with the help of this line, I can do the prediction. Okay. So that is one use. Another use is that if you want to compute any intermediate value, means say for example, your one data is here, one data is here, but in between, for any value of x, if you want to calculate what will be the y, so if the equation of the line is there, a and b are not corresponding to x, you can predict the value of. So here, as you can see, uh, it is a indication of negative correlation. Okay, as x increases, y decreases, and this is the situation if all the points lie on the straight line. Okay, if all the lines falls on this straight line, then the correlation will be 1. There is a perfect linear relationship. In that case, r is equal to 1. And similarly, if the value falls on this line, r is equal to minus 1. Now, these two cases indicates that if your all these data looks like this, okay, say it is in form the circular. So in this case, r will be 0. And here, if you plot the data and it is in this form, say it is basically uh, like this. Okay, so here like this. So in this case, r equal to 0. So these are some visual representation. So we have developed the theory for the joint probability mass function, and we have seen that how to find out uh, marginal marginal probabilities, that probability mass function, conditional. We have discussed the concept of independency. If they are not independent, how to find the covariance, and then how to measure the relationship between y and x and y in terms of the correlation coefficient. Then similar theory is there when x and y are not discrete random variable, rather they are jointly continuous random variable. So the concept of joint density functions comes into the picture. So uh, theory is more or less similar, only the summation, in place of the double summation, you have a double integral, and in place of the joint probability mass function, you have a joint density function. So here, uh, x and y are jointly continuous random variable if there exists a function fxy. Okay, in the case of single random variable, we have a probability density function. So here it is basically it is called joint density function. So x and y are jointly continuous random variable if there exists a function fxy defined for all x and y, having the property that for every set C, okay, C, you will see at a later stage, C basically consists of the two intervals, one for x, one for y. For every set C of the pair of real number, the xy uh, is written together belongs to C is the double integral over C fxy dy dx. So fxy here it is called the joint density function of the random variable x and y. So we have a pair of random variable x comma y, as you have seen here. Here usually we write x comma y. Okay. So here, so since it is a joint density function, as I told you that this value will be non-negative, fxy is non-negative defined for all x and y, and the double integral over minus infinity to plus infinity, minus infinity to plus infinity, fx dy dx will be 1. So as I told you that what it represents the C basically the two intervals. Okay, so x lies between a and b, y lies between c and d. So probability that x lies between a and b, y lies between c and d is nothing but integration of fxy dy dx, and y varies from c to d and x varies from a to. So once we have a joint density function, we can find out the marginal density function. If I integrate the joint density with respect to y, then we get marginal of x. If I integrate fxy with respect to x, then we get the joint density function of y. So these are known as the marginal density function of x and y. So from the joint density function, one can always find out the marginal density function of x and marginal density function of. So here also, if x and y are independent random variable, then the joint density function is equal to the product of respective marginal density function. So for x and y to be independent, we have to check that if two random variables are given. So if we have to check that whether they are independent or not, so in that case, we have a joint density function. We have to find out the marginal density function of x, marginal of y, and we have to verify this equality. If it is satisfied, then we say that x and y are independent. Otherwise, no. So I'll take up one example to show you. Say joint density function of x and y is given. Okay, so it is 1 by 28, 4x plus 2y plus 1, and x varies from 0 to 2, y varies from 0 to 2, 0 other one. So mostly basically you have to use the result of the double integral, which you have already done. So one thing is that suppose I want to verify that whether it is a valid density function or not. So in that case, as you can see, we have to integrate this. This is the domain. Basically, x varies from 0 to 2, y varies from 0 to 2. Okay. So it is 1 by 28, 4x plus 2y plus 1 dy dx. So y varies from 0 to 2, x varies also from 0 to 2. So in many cases, you may have a different types of domain, and accordingly, we have to find out the lower limit and upper limit of the respective variables that we have to integrate. So I'm not going to work out this, but as you will see that after evaluation of this integral, the value is coming 1, so it is a valid density function. From here, if we have to find out marginal, so fx and fy. As I explained you in the beginning, that each subscript indicates that you are finding for x, this indicates you are finding for y. Okay, so the marginal density function of x is denoted fx of x. So you have to integrate this with respect to y. So the joint density function, and then you have to integrate with respect to y. So y varies from 0 to 2, so 0 to 2. So this is the value which I have written. You can check whether it is correct or not. Similarly, once you get fx, if you want to check whether it's a valid density function or not, you can integrate 0 to 2, 1 by 14, 4x plus 3 dx. It should come 1. Similarly, you can get fy. So now you are integrating with respect to x. So x varies from here to here. Okay, so 0 to 2. So it is 2y plus 5. Now, if I want to, as you can see, these are x and y are not independent. Okay, x and y, because the joint density function is 1 by 28, 4x plus 2y plus 1, and marginals are fx and fy. So if you multiply, these x and y are not independent random. Okay, so in that case, we need to find out if I need to find out, or you have been asked to find the correlation coefficient. So the correlation coefficient, we have already defined the rho, which is equal to covariance xy and then sigma x, sigma y, sigma x, sigma y. So to find the covariance xy, we need to compute exy, ex and ey separately. So expected value of xy will be, this is the way, as I told you in the beginning, that xy you are right here. This is the joint density function you have to write, and then dy dx. So integration of y 0 to 2, x varies from 0 to 2. So if you simplify, it will come 9/7. You can check all these expressions, all these calculations. So expected value of x, since we have found out the marginal density function of x, we can get here x into fx dx. So it is 25/21. Expected value of y, we have to get it. So y into fy dy, this is 23/21. Now we have to get variance of x. So what is the variance of x formula? Variance of x is expected value of x square minus e of x square. So this is the expression. As you can see, this is the expression for variance of x. So in order to find variance of x, we have to find e of x square. And e of x you have already obtained. So expected value of x square, you have to x square, and this is fx dx. So this is 12/7. So variance of x, you can simplify and get it. Here I have simplified. So anyway, similarly, you can get e of y square and then variance of y. So covariance xy, you can calculate, which is coming minus 8/441, and ultimately you will get the correlation coefficient, which is coming minus 0.058. So correspondingly, when the joint density function is given, we can compute the correlation coefficient between x and y if x and y are not independent. If they are independent, then covariance will be 0, and hence the correlation will be 0. So these are how the correlation is computed. Correlation means population correlation when x and y are jointly continuous random pair. Now the conditional density function, just like we have defined the conditional probabilities, that probability x equal to x given y equal to y. So similar to that, here we have a conditional density function. So conditional density function, basically it has a notation. So it is fx y x given y, that the subscript represents x given y, means we are dealing with the conditional density function of x given y equal to y, and these are the dummy. Okay, so how it is defined? It is defined in a similar way. So joint density function divided by the marginal of y. Okay, and fy has to be non negate greater than g. Similarly, conditional density function of y given x. Okay, this was the conditional density function of x given y equal to y. Here it is the conditional density function of y given x equal to x. So again it is fxy divided by the marginal of x. So the variable which is used, that given, that will come into the denominator. Okay, because here you have conditional density function of y given x equal to x. So that is there. So once we have obtained the conditional density function, we can get the conditional expectation. So conditional expectation, we write expected value of y given x equal to x. Okay. So this, since the conditional density function is known, we can easily find out conditional expectation. So it will be y times y into the conditional density function. Okay. So this, when you will simplify, it will be a function of x. Okay. Because this is the variable which is used as a conditional. Conditional means given. Okay. So expected value of y given x equal to x will be a function of x, and it is known as regression of y on x. Okay. And this quantity is known as the conditional mean. Conditional expectation means conditional mean. Similarly, x given y, we can calculate expected value. This is the conditional mean of x given y equal to y, and this is also known as the regression of x on y. Okay, so it is x into conditional density function of x given y. So it will be a function of y, because uh, here we have used conditioning on the variable y. So it will be a function of y. So I will show you by means of the example that how these quantities are computed. And uh, so let us take the previous example. In the previous example, we have this. We have already used the density function is given. So here, if I need to find out what is the conditional expectation, so in order to find the conditional expectation, what we have to do, we need to find out. We need to find out this quantity E of y given x. Okay. So in order to find this, we need to find out the conditional density function of y given x. So fy x. So it is fxy, fx of x. Since this is known to you, this we have already computed. So we have kept here fxy, and this fx of x we have substituted. So after simplification, you will get this quantity. Okay. Now we need to find out the conditional expectation. So from here, okay. So now we need to find out this quantity. So E of y, this is E, this is E, y given x. So y and into this quantity. So okay. So fx, fyx, okay, this you substitute. Okay. So substitute. So you, after simplification of this integral, you will see that you got at 8x plus 22 by 3, 8x plus 6 denominator. Now this whole quantity, as you can see, it is a function of x. Okay, it is a function of x. No y is appearing. So for any given x, okay, for any given x, say for example x equal to 1, okay, because x varies from 0 to 2. So for any particular value of x, I can find out the conditional mean. So say for example x equal to 1, x equal to 1 is substituted, and you will get the value 23 by 20. So there is a similar concept of the joint cumulative distribution function. So in short, it is defined as the capital F x comma y. So x comma y uh, indicates that you are dealing with the two random variable x and y. So the CDF of x and y is probability x less than equal to x, y less than y for all x and y. So in terms of the joint density function, it is minus infinity to x, minus infinity to y, fts ds dt. So if these can be differentiated with partial derivative. So if you take the partial derivative with respect to x and with respect to y, then you get the joint density. So all the other concepts will come, that whether the function is differentiable or not. Partial, concept of partial derivative will come. But in most of the cases, if you have the joint CDF, you can find out the joint density function. So as I was telling you, at the end I gave you the derivation of the least square. So I'm not going into the detail. These are the points, and as I told you that these are the scatter diagram, and this is the line which we need to fit. Okay, which y is equal to a plus bx. So we have to find the intercept and we have to find the slope with the help of these data. Once a and b are computed, say a equal to 2, so the line is known to. So to fit the line, as I told you that we have the error y minus yi ahead, and sum of square of the error we write, which is y minus a minus bxi. So in order to minimize the least square, it says that you uh, differentiate with respect to a, that take the partial derivative with respect to a and b equate to 0. So this is the procedure we follow, and ultimately you can derivations are nicely done, so you can go through. And since it has been done in maths 2, so there is no need to again discuss. So these are known. We have got two equations. So one is this, one is another is this. So two equation, two unknown, simplify. So that also I have explained. So ultimately you get the value of b, which is slope. And once b is known, you you use this relationship, divide by your data, the first equation. So a plus bx bar. So b is known, so a you will get using this quantity. So usual steps when the data is given. So sometimes it is easier if you are doing it by hand or calculator. So you have a xi, x1, x2, xn, yi, y1, y2, yn. So you if your objective is to find only b, so in that case you need xi square, xi, yi. So in one column you compute the x1 square, x2 square, xn square. Other column you compute the product x1 y1 x2 y2, and finally this. So sum this column, and if you need to find out the correlation also, then another column you have to make. So using this and substituting the values in the given formula, you can get b and a, and you can also get the correlation coefficient. So all these things have been discussed, so I'm not going into detail. Uh, so, so one more example I will explain you. Say uh, a local radiator manufacturer subjects his radiator to two tests. Okay, so a company who is making the radiators, as you know, is used in the engine, basically the car engine. So they put the radiator under two types of test, and the function that describes the percentage of radiators that pass these two tests. Okay, so percentage of radiator. So it is 8xy 0 otherwise, and y is less than x, less or equal to x. So this is the domain. Okay, so joint, basically you are given the joint PDM. The random variable x represents the percentage of radiator that pass test A, and y represents the percentage of radiator which pass test B. So x, what is x and y, that has been given to you and has been defined, and their joint density function is defined. So first thing is that we have to verify. Say suppose I remove 8, okay, and simply I put it as a k in place of 8, okay. In place of 8, suppose I put some c. Uh, in place of 8, if I put say k, and I say that uh, fxy is a valid density function, so determine the constant k. In place of 8, if I put in place of 8, if I put k, so it is basically k xy xy. So find the value of k. So what you have to do? You have to integrate. So here it is here. So first thing is that we have to identify the domain. So as you have seen, the what is our domain? 0x 0 y 0 less or equal to y, less or equal to x, less or equal to 1. So this domain is identified in this. This is the y equal to x, y is less than x, x varies from 0 to 1. So this shaded region represent the domain of the density function. So we have to integrate this in order to get the value of k, or in order that you have to verify whether it's a valid density function or not. So as you can see, it is a double integral. So y varies from 0 to x, that red line, y varies from here to here. Okay. So 0 to x, and x varies from 0 to 1. So if you simplify this integral, it will come 1. Now you have to get the marginal density function of x. So you have to integrate with respect to y. Okay. So y varies from 0 to x. So you get this one. I'm not doing the calculation, so you can verify easily. It has been done here. Similarly, if you have to find the marginal of y, then what you have to do? We have to integrate with respect to x. So x varies from y to 1. This one. Okay. X varies from, this is the line y equal to x. So x varies from y to 1. So x varies from y to 1. So you have got 4y, 1 minus y square, and y has to be less than 1. So range we have to write. Now, as you can see that x and y are not independent. So in order to check the independency, what we have to do? We have to write this fxy into the product of marginal of x, marginal of y. So 8xy is not equal to 4x cube, and this is another factor. So x and y are not independent. If they are not independent, we need to find the correlation. If you are asked, so you need to find E of y square, E of x, covariance, etc. So ultimately you will get rho equal to 0.49. So one example I explained you that given the joint probability mass function, how to get the correlation coefficient. Another example, here I am showing that how to get the correlation coefficient in the case of the joint density function. So in most of the problems related to joint density function, is clearly identifying the domain. Okay. So once you have identified the domain, you know that how to solve the double integral, because it is a part of your maths 2 course. So rest of the calculations becomes standard. Okay. So this covers the concept of the joint density function. In the next class, we will be discussing exclusively the bivariate normal distribution. So the theory which we have used, that will be uh, used to get the results related to bivariate normal distribution, and we'll see that how to compute the requisite required probability using the tables of the normal distribution. So all these things we'll discuss in the next two classes. Okay, so I will stop here. Is that fine? We have uploaded an assignment sheet on joint distribution on the Moodle. Okay.
Sir, when did you say was the last date of submission for that assignment one?
Everybody is saying that you are busy with